Welcome to the Introduction to Magnetism and Electromagnetism. In this chapter, we will explore the fundamental concepts of electric and magnetic fields, their properties, and their interrelationship. These concepts are essential to understanding electromagnetism and a wide range of phenomena in physics, and are crucial for the development and operation of many modern technologies. Electric fields are the regions around charged particles where other charges experience a force. These fields are represented by lines that indicate the direction and strength of the force. Coulomb's law helps us understand the relationship between two charges and the force they exert on each other. The formula is given by F equals K sub E times the absolute value of Q1 multiplied by Q2 divided by R squared. In this formula, F represents the magnitude of the force between the charges. Q1 and Q2 are the magnitudes of the charges involved. R is the distance between the centers of these charges, and K sub E is Coulomb's constant, which is approximately 8.99 times 10 to the power of 9 Newton meter squared per Coulomb squared. Magnetic fields are regions where moving charges experience a force. These fields are represented by lines that indicate the direction and strength of the magnetic field, forming closed loops. The Lorentz force law describes the force on a charged particle moving through a magnetic field. The formula is given by F equals Q times the cross product of V and B. In this formula, F represents the force experienced by the charge. Q is the magnitude of the charge, V is its velocity, and B is the magnetic field vector, which indicates both the direction and strength of the magnetic field. When an electric current flows through a conductor, it generates a magnetic field around it. The direction of the magnetic field can be determined using the right-hand rule. If you point the thumb of your right hand in the direction of the current, the curl of your fingers shows the direction of the magnetic field. The magnetic field B around a long, straight conductor carrying a current I is given by the formula B equals mu naught times I divided by 2 pi r. In the formula, B is the magnetic field in teslas, mu naught is the permeability of free space, approximately 4 pi times 10 to the power of negative 7 Tesla meter per ampere, I is the current in amperes, and R is the distance from the conductor in meters. For example, if a wire carries a current of 5 amperes, the magnetic field at a distance of 0.1 meters from the wire is calculated as B equals 4 pi times 10 to the power of negative 7 times 5 divided by 2 pi times 0.1, which equals 10 to the power of negative 5 teslas. Magnetic circuits are analogous to electric circuits. They consist of magnetic materials and air gaps through which magnetic flux flows. This concept helps in the analysis and design of devices like transformers, inductors, and electric motors. Magnetic flux, denoted by phi, is the measure of the quantity of magnetism, considering the strength and the extent of a magnetic field. It is measured in Webers. Magnetic flux density, denoted by B, is the amount of magnetic flux through a unit area perpendicular to the direction of the magnetic field. It is measured in teslas. The formula is B equals phi divided by A. In the formula, B is the magnetic flux density, phi is the magnetic flux, and A is the cross-sectional area through which the flux passes. For example, if a magnetic core has a cross-sectional area of 0.01 square meters and carries a magnetic flux of 0.2 Webers, the magnetic flux density is calculated as B equals 0.02 divided by 0.01, which equals 2 teslas. Faraday's law of electromagnetic induction states that a change in magnetic flux through a circuit induces an electromotive force, or EMF, in the circuit. This principle is the foundation of many electrical devices, such as transformers and electric generators. The induced EMF in a coil is given by the formula E equals negative N times the rate of change of magnetic flux. In this formula, E is the induced EMF in volts, N is the number of turns in the coil, and d phi by dt is the rate of change of magnetic flux in Webers per second. For example, if a coil with 100 turns experiences a change in magnetic flux of 0.05 Webers over 0.1 seconds, the induced EMF is calculated as E equals negative 100 times 0.05 divided by 0.1, which equals negative 50 volts. Lenz's law states that the direction of the induced EMF and the resulting current in a closed loop is such that it opposes the change in magnetic flux that produced it. This is a consequence of the conservation of energy. Lenz's law can be understood by considering the negative sign in Faraday's law equation. The induced EMF generates a current that creates a magnetic field opposing the original change in flux. For example, if the magnetic flux through a coil is increasing, the induced current will flow in a direction that creates a magnetic field opposing the increase. Conversely, if the magnetic flux is decreasing, the induced current will flow in a direction that creates a magnetic field supporting the flux. Understanding magnetism and electromagnetism is crucial for electrical engineering. These principles are applied in various devices and systems, from simple inductors to complex electric motors and transformers. By mastering these concepts, students can better understand and design electrical and electronic systems.